podcast is brought to you by LMU Munich.
Okay, good morning. So we have, actually, I have a lot of material to cover, but okay, let me try to cover at least some points which I think are maybe not more important, but okay, so more logical in this context. So I want to move now to gravity, okay, and try to visualize this picture from gravitational point of view, okay. Now with gravity, we can be more ambitious in the sense that, of course, with this holographic system that I presented, obviously that system is non-gravitational, so the only thing that it shares with gravity was attractive momentum-dependent interaction. And despite this fact, as we saw, it reproduces a lot of things that are surprisingly close to what we know about black holes. But of course, from the point of view of information processing and storage. So I had this checklist. I will not repeat it, but okay, virtually every aspect is there, which is very surprising, and that makes us, or at least makes me think that the laws of information are universal. And so there are certain things that are not specific to gravity, but okay, gravity is still very special. Okay, so now I want to go to gravity and then try to understand. Once we think of these constituents, the quanta that we had in the form of this field psi, there are even more properties that we can understand in that case. Okay. So what is gravity from the point of view of a particle physicist? Gravity is an interaction that is mediated by a messenger that has certain specific properties. So this is spin 2 equals to 2 and mass equals to 0. Okay. Now, as I said, when we discuss different systems, the important thing is to identify degrees of freedom. If we are thinking from the point of view of particle physics and from the point of view of effective theory, okay? And then the question was how to label these degrees of freedom. And useful labels are, of course, labels that tell you how these degrees of freedom transform under the symmetries of your vacuum and under the symmetries of your Hamiltonian, of your Lagrangian. Now, in this description, we will identify as vacuum what we normally call Minkowski vacuum. So we will be in the sort of, we will think from the perspective of an S-matrix observer. So observer that can define consistently in states and out states. So this observer is super powerful, so can set up an experiment in which you have in states coming in, t equals minus infinity, let's say forming a black hole, and then moving out to t equals plus infinity. And obviously, from the point of view of this observer, the labels are the ones which are symmetries of Minkowski vacuum. So Poincare symmetries. So the transformation properties of this labels, so will indicate how the the degrees of freedom transform under this Poincare symmetry. Poincare symmetry has two Casimir operators, the spin and the mass. And so that's why we classify particles according to their spin and mass. So this is a very special representative, graviton, what we call graviton. So it has spin 2, mass equals 0. So therefore, you can introduce gravity in several different ways, and you end up with the same thing. So you can understand gravity as dynamical geometry. That's one way of introducing gravity. Okay. But another way to introduce gravity is, as I said, to try to introduce a consistent theory of a spin 2 massless particle. Okay. So spin 2 massless particle, you want to build a theory of it. And that gives you the same result. So in both cases, if you do a self-consistent construction, you will end up with Einstein gravity. Okay? So in other words, if you demand that you want your theory to propagate a single degree of freedom of these properties, that's Einstein gravity. That kind of theory always flows to Einstein gravity at sufficiently low energies. Okay? Okay, of course, above certain cutoff, you can introduce other degrees of freedom. They will be important at high energies. Okay? So now let's therefore introduce a theory, and let's try to understand some basic properties of this degree of freedom. Okay? Graviton with spin 2. So there is a so we can work as usual. We can start with the linearized theory. Okay? A linearized theory means that we work in weak field approximation. So in other words, if you think of a full metric and deviation around this full metric of your degree of freedom, so this deviation should be less than 1, much less than 1. Of course, this, if you think in terms of general covariance, these things are obviously frame dependent. And if you want to think in those terms, you can always choose a convenient frame to get rid of the effect of the rest of the universe. This is, for instance, what we are doing when we are measuring gravitational force of Earth. We are going in reference frame in which Earth and us are experiencing a free fall in the gravitational field produced by the rest of the universe. Okay? And in that, if you go to that reference frame, for instance, the gravitational, so the deviation from the Minkowski metric produced by the gravitational field of the Earth is very small. Okay, so it's approximately, this object is approximately 10 to the minus 7, something like that. And now, if Earth were a black hole or close to a black hole, then on its surface, in that case it would be a horizon, the deviation would become order 1. So this is one way to think about a strong gravitational field produced by a macroscopic black hole, let's say. So it produces the deviation from Minkowski metric, which is order 1. Okay. So now, so let's try to understand the simplest things about graviton. Okay. So gravitational field, weak field approximation, some ripples on top of Minkowski vacuum. Okay, so they satisfy an equation that turns out to be so this is okay. Free satisfies the free equation, but they satisfy an equation with a source. So for a moment, yeah. Okay, let's. Where this is a tensor, which turns out to be a linearized version of Einstein tensor. Okay, so if you go two ways, so you can start with Einstein gravity, which is a theory of dynamical geometry, and you can linearize it on top of Minkowski metric. But you can go bottom up. You can simply ask that you want to formulate a consistent theory of spin 2 with mass 0. And again, you cannot write anything down other than linearized Einstein tensor. Okay? That's the only consistent theory of a linearized spin 2 massless. Okay? So let's study it a little bit. So the Einstein tensor has the following form. Sorry for technicalities, but they are important to illustrate certain points, because there are two important things. One is that we need to watch is, one is gauge redundancy, okay? And the other thing is quantum to classical story. Classical transition. So now it turns out that theories, particle theories of particles with spin starting 1 and higher, the formulation is always gauge redundant. Okay? Now, the redundancy normally is telling you that you are using certain redundant variables to describe a physical phenomena, right? And so you can ask this question whether redundancy is fundamental or it's just because we are not powerful enough to find correct variables to describe physics. It looks like that redundancy is fundamental, okay? So somehow it's built in theories of spin already starting from spin 1 and higher. Well, even spin 0, you can rewrite in a gauge redundant way. So spin 0 particle, pseudo-scalar, you can rewrite as an antisymmetric tensor, b mu nu, it's a dual to that, and b mu nu is a gauge redundant theory. So even for spin 2, for spin 0, the story is somehow, it also feels gauge redundancy in certain sense. So, and so that's the point. So that's where we are, that we see that gauge redundancy plays a fundamental role in formulation of those theories. Now, okay, so let's study a little bit this theory. So H is just a trace, okay? The indices are contracted through the flat space metric. And there is a coupling constant, of course. If we want to, once we canonically normalize H mu nu, there will be a coupling constant, Planck mass. For a moment, I'm setting it to equal to 1. Okay? So there is this thing. So first, let's study this, and then we can ask this question: why this and not something else, right? Now you can see immediately that this. Wait a minute. So you can see immediately that this theory exhibits redundancy. Where psi nu is a vector. So you can shift it as a symmetrized derivative of a vector. And this gauge redundancy is important, of course, because we need to understand what does this theory describe. In other words, the first thing that someone gives you a theory, what you need to understand is that how many real degrees of freedom are there, okay? How many of them are unphysical? How many of them are physical but non-propagating, Okay, non-propagating means that you can have a degree of freedom which is physical in the sense that it could respond to a source, okay, but it doesn't have its own life. It's not non-propagating. And then how many are propagating, right? So we need to understand this. So therefore, we have to stare a little bit at this expression, okay, and try to bring it into a form which is manageable, okay. First of all, if I want to find a propagator for graviton, I want to bring equation in the form that there is some kind of invertible operator, right? So this is not terribly nice operator the way it is. So we have to use gauge redundancy to eliminate certain unpleasant things, okay, to make it more convenient. So we can fix the gauge. The convenient one is this, the Donder gauge. And with this gauge, you can simplify the story, okay? Because now, so the things with box, I will leave for a moment. So what do we have here? This term will give me, right? This one, the same here. This will cancel this. So this thing will get cancelled. So therefore, and this will get converted into 1/2 of a box, right? Okay. And okay, so now we can rewrite it in a little bit better form. So I have 1/2 here, minus one there, so minus 1/2. Okay, and now we can eliminate the trace by taking trace of this expression, right? So if I take trace of this expression, I'll get trace from here. I get minus 2 trace from there, and this is trace of t. I mean, t being trace of t mu, and certain symmetric tensors. For a moment, I don't know what it is. Okay, and so we can express box H, right, as minus t, and then plug it back there and take on the other side. Okay, and we get this nice form. So now, of course, we can invert this operator. It's nice box cell inversion, and study how this excitation, this particle or this field reacts to a source. Let's count the number of degrees of freedom, okay? Right? Because we fix the gauge, we eliminate a certain number of degrees of freedom, right? So naively, it looks like at the beginning, how many are there? We have symmetric tensor, 10, right? So naively, it looks like there are 10. This eliminates certain number. How many?
4.
Yeah. By the way, how do I know that I can bring the story to this gauge? Okay. Right? I told you, but you should not take it for granted. Because you can check that if, let's say, there is original one that doesn't satisfy this gauge, okay? Which means that for the original one, the story, this object, is non-zero. Okay? Now I can do transformation with this parameter. All right? And see whether I can always choose this parameter, okay, in such a way to satisfy this equation for the transformed age. And you can always do that. Why? Because the equation, if I do this, will have a form of box psi sourced by something that is a combination of h. So which means that, and this always has a solution, because this is just simply Maxwell equation for psi, okay? Okay, so now, so we kill the set of degrees of freedom from here, okay? We are left with 6, but there is additional remaining gauge redundancy, okay, that this leaves us, because we can use resulting gauge redundancy on shell, okay? So there is a similar gauge redundancy, but on shell with psi that satisfies free equation. Why? Because here psi, this condition is not offset if I shift psi by anything that satisfies free equation, right? Okay, so and we can use that residual degree of freedom to kill 4 on shell, and we are left with 2, okay? So there are 2 physical degrees of freedom that are described by this field propagating, okay? So far everything is fine, right? Very good. So now, the thing is, okay, if you give me a source, I can understand how the source reacts to how h mu reacts to the source, right? So now what you can do is the following thing, right? So let's say you can have, for instance, let's think in terms of some kind of what kind of interaction this field h mu mediates between different sources, okay? So a source and a probe, let's say, I don't know, Earth and us, or a moon, or whatever, okay? Right. So then what happens? So I can have a main source, right? So classically I can find it, no problem, because I can first find a gravitational field created by the main source. So let's say I have T mu nu as a source, and I have a tau mu nu as a probe, right? Okay, so I can find h mu nu created by a source, right? So this is simply 1 over box okay, and then convolute the probe with this gravitational field produced by this gravitational field, right? So then effective action of the probe in this gravitational field, right, of the probe will be convoluted with this, right? Okay? So in other words, I have a probe, and this creates a gravitational field, and then I have a source. This is T mu nu. And this creates gravitational field, tau mu nu, h mu nu. And then this gravitational field dictates a probe what to do, okay? To follow geodesics, whatever. But notice that this is the same thing as if I would compute, in a quantum theory, one graviton exchange amplitude, okay? So this is literally a one graviton exchange amplitude. Indeed, I mean, if I do this story and I find a propagator, okay, of the source, of the gravitational field. So generic propagator, right? I will not repeat the story. Will have the form, right? So propagator that mediates this is and this is just simply one graviton exchange by a particle with this propagator. This object there is simply okay, so why? Because this part of the story, is simply h nu produced by the source. This is this, okay? So this part is simply this solution, okay? Okay, so this makes the first contact between theory of classical theory of linearized gravity and one particle exchange amplitude by a massless spin 2 quantum particle. Okay. Now this may sound a little bit surprising, right? Because you can say, how can it be that the quantum exchange gives me the classical result, right? But this is not surprising because in this process we didn't consider any loops, and secondly, this is a three-level process. But three-level process can also be quantum perfectly nicely, okay? But the external sources are classical, okay? So, and this is important. In other words, we're not considering situation in which an external graviton is emitted. Of course, if external graviton is emitted, even a three-level process, it can be fully quantum because obviously, let's say Gravitational, in a process in which you emit a single graviton, obviously that process is a quantum process. It's not a classical process. Okay, but here this reduces to a classical story because this is graviton only appears as an intermediate state and appears at the three level. Okay. Any questions about this? All right. So everybody is happy. Very good. So now, what else? Okay, so now the thing is, what can we learn from if we stare at this expression, right? What can we learn about the nature of gravity? Actually, you can learn a few things, right? Already from this linearized story. Actually, a lot of things. Now, one of the things is that if source is normal, okay, if source has normal energy density, positive, if source doesn't violate so-called energy conditions, then the following is clear, that among the sources with positive pressure, the interaction always will be attractive, okay? Now, you can have sources which make sense and they have negative pressure, okay? And among such sources, the story may be different. For example, sources for which you can have, for instance, a source of the type, let's say, a cosmic string, for instance, okay? So cosmic strings are these one-dimensional objects, okay? So they are strings, and they have the property that, okay, first of all, they are boost invariant in one dimension. So these are because these are one-dimensional objects, they have word line. They are word lines. So sorry, they are word surfaces because it's a word sheet, okay, two-dimensional. And so they are boost invariant, okay, along their word volume. And so the energy momentum tensor that they have is localized. Let's say if I take a string that is oriented along z-axis, okay, and is localized in xy direction, all right, so this would be some kind of a delta function in xy. And with certain tension, okay, certain parameter, constant, some let me call it mu, and the energy momentum tensor, which is boost invariant in tz direction, okay. And this boost invariance demands that it must have a negative pressure, okay. And this is general property. So for extended objects that are boost invariant in their word volume, that obey, they, from the point of view of an observer, outside observer, they have negative pressure. Okay. Well, from the point of view of any observer. So for instance, because of this, the story is no longer true that gravity is attractive among extended objects because pressure compensates. And actually you can do this exercise, very nice. If I take this energy momentum tensor and plug it here in this exchange, okay, this exchange basically will have a form, right, of 1 over box, tau mu nu, 1 over box, convoluted with this, right? And it cancels out. So there is no Newtonian part of the force, okay? Because the pressure compensates. So pressure is repulsive and compensates the attraction generated by the energy density, and so they cancel, okay? You can go even further. So for instance, you can have, instead of a string, we can consider a two-brane, okay? So with a two-brane, let's say two-brane localized in x direction, right? So with two-brane, we'll have even more negative pressure. And actually, in this case, pressure takes over, and two branes, they repel gravitationally, okay? Already at the linearized level. And there is one famous object with negative pressure that really repels everyone. That's cosmological constant, right? Positive. The cosmological constant would be simply this, right? In this approximation, right? And that has negative pressure, and that's why you know all these discussions about dark energy. We are observing observationally. We are entering in the accelerated epoch in the universe, and one explanation could be that there is some sort of a source with a negative pressure like this. Okay. All right. So now, however, for the normal sources, interactions among particles, because particles they have non-relativistic particles, they have zero pressure. Relativistic ones, they have still positive pressure, right? So among normal particle-like sources, among localized objects, gravity is always attractive, okay? So from the point of view of elementary particle interactions, gravity is attractive. So therefore, now this force that is mediated by gravity among particles, you can derive from this expression actually. So what you need to do, you have to plug in the energy momentum tensor of whatever particle you like. Okay, you take standard model. For instance, you want to understand what is to the leading order. interaction between a W boson and the Higgs, okay, through the exchange of graviton. You take energy momentum tensor of W boson, and to that order, okay, and that's what will give you the gravitational interaction at the level of one graviton exchange among elementary particles, okay? Now, what about self-interaction? Of course, because gravitons, they themselves, in this construction, so don't get confused with the geometric picture, okay? So here we are building theory block by block from the elementary particle point of view, okay? So in this picture, of course, gravitons, they also have energy momentum tensor, okay? And they, to the next order, we are obliged to take into account the coupling, self-interaction of the graviton with its own energy momentum tensor, okay? Now, the expression for the energy momentum tensor of the graviton I will not write because it's complicated, but okay, it's so for energy momentum tensor for graviton in this order, okay? This is contains series of all possible things like with all possible contractions, with a very specific one, right? But we will fish out the key points from here, okay? So now the point is, therefore, this is the way you can build up general theory of relativity bottom up. So I can now demand that to next order, a graviton interacts with its own energy momentum tensor. And do this, continue this iteratively, and I will get infinite series. And this infinite series will be equivalent of the expansion of the Einstein's general theory of relativity. On Minkowski background, of course, we are on Minkowski background, okay? So therefore, we can recover GR all the way up to a cutoff, of course, all the way until it becomes strongly interacting. We'll discuss now at this point. Okay, we'll recover GR by doing this procedure iteratively, self-consistently coupling in each order graviton to itself and to the rest of the species. Okay. Okay, so therefore, now what we can fish out from here for important thing will be that there is a vertex, right? So therefore, effectively there is a vertex already in the next order, okay? And there is some effective coupling strength that controls this vertex. And now we restore Planck scale back, okay? Now, of course, if we want to canonically normalize graviton, then let me see, where should I write? So if we want to canonically normalize graviton, of course, this is dimensionless, so that's not a canonically normalized field. For canonically normalized graviton, this is the correct expression. In the units where h bar is 1 and c is 1. Okay, so there is this fundamental energy scale which controls the strength of the interaction. All right, so now, so therefore, you can see already from here, from the structure, that this strength, this is first order in 1 over m Planck, okay, and quadratic in derivatives. So it goes like p square, okay, over m Planck. So p square being some characteristic momentum transfer, which I explain in a moment, okay. So this is the strength, this vertex. Now, for for particle physics perspective, it's more convenient to think in terms of 2-point interactions, so 4-point interactions. So okay, 2 by 2, because the trilinear vertex is an elementary vertex. But what is a better characteristic of a process is how important is 2-to-2 scattering. Okay, so in other words, how two gravitons can see each other, or two photons can see each other through the exchange of a graviton. Okay. Now, of course, you can build this already to this order because you can. I'm out of space. Okay, let me put this up. Already to this order, we can build an effective vertex. So in the next order, there will be directly a 4-point vertex. Okay, and in both cases, the effective interaction strength we can characterize by effective alpha, sort of analog of the electromagnetic coupling constant, a dimensionless number. So it's always good to parameterize the strength of an interaction by a dimensionless number, okay? Because at the end of the day, in physics, we compare dimensionless numbers. And this is alpha gravity. And this goes, of course, as certain energy scale, which essentially is a characteristic momentum transfer in your process, scaled by Planck mass. By Planck mass squared. Okay, so this is alpha gravity. You can also rewrite it differently. You can also rewrite this as the Planck length. So, sorry, I didn't say. We are in 3+1 dimensions for a moment. Everything is generalizable to with appropriate power of m Plancks to arbitrary dimensions. Over lambda squared, where lambda is the length. What is it? It's the de Broglie wavelength of characteristic momentum transfer, okay? So this immediately tells you that if gravitons have low momenta, okay, or if they have long wavelengths, they interact extremely weakly. Now, that's why we normally say that at the level of elementary particle physics, let's say in the standard model, we say that gravity is not so important. And indeed, that is true because, for instance, if I take gravitons of 1 centimeter wavelength, I ask this question, okay? If I have gravitons of 1 centimeter wavelength, what's the typical characteristic strength of their interaction? Okay, would be enormously suppressed because this would be something like, for lambda, about a centimeter, because Planck length is approximately 10 to the minus 33 centimeters. So for a centimeter wavelength, this would be something like 10 to the minus 66. Okay? So in other words, if you put two 1 centimeter gravitons in this room, and ask how long you have to wait before they see each other and they interact with each other, this exceeds the age of the universe by an enormous factor. Okay? They never see each other, basically. Now, what do we learn from here? We learn from here an extremely important thing, that in everyday life, for gravitons that are long wavelengths, okay, the only important effects can be collective effects. Okay, so you can see gravitational effect only if they are a lot. Okay, then you can see it, but otherwise the gravity is so weak that the quantum effects of individual long wavelength gravitons are extremely small. Okay, however, there is another side of the story, that this expression also tells you that for high energy collisions, where momentum transfer is high, so for high momentum gravitons, interaction becomes strong very quickly. So interaction grows quadratically with momentum transfer, okay? The power law, it's a power law growth. And becomes strong at around the Planck mass, okay? Now, that's the problem with quantum gravity. What is the problem with quantum gravity? The problem with quantum gravity, the main problem with quantum gravity is not that you cannot think about gravitons as quantum. Of course, you can think about gravitons as quantum. We can linearize the theory, quantize it, okay? So, no problem. But the problem with gravity is that gravitons become strongly coupled in ultraviolet. Okay, so there is an ultraviolet scale, Planck mass, where gravity becomes strongly coupled. And it's a problem of strong coupling because we don't have good enough apparatus to compute all processes in a controllable way at the strong coupling. Okay. Now this, of course, the core of the issue is that the gravitational interaction is controlled by Planck mass. Okay, so gravity is not renormalizable. In other words, the interaction between graviton and its own energy momentum tensor is not a renormalizable interaction already at the cubic level. And this, of course, also gives us questions of loop corrections. However, questions of loop corrections, at least we have idea where to go, in which direction, because we have string theory for that. So string theory takes care of this, at least in string perturbation theory, okay, of loop corrections. Okay, any questions so far? So everybody is happy with everything. It's incredible. Now.
So you said something about higher dimensions?
Yeah.
You would have other components of the metric?
No, of course, they will propagate more degrees of freedom. That of course is true. But the structure of the interaction. Remember, I told you that there is this relation between the Planck length in d dimensions. D minus 1 is h bar g Newton. Remember, in that dimension. So correspondingly, of course, this tells you that the gravitational coupling, instead of m Planck square, you will have m Planck in power d minus 1 correspondingly, okay? So that will change the scale. So, right, and of course it will acquire more degrees of freedom, absolutely, yeah. Yeah.
Will there be a correction in alpha gravity if we are strongly coupled? So we have said that it is power law p squared, but at some point it should have another form. So could it also be that it's just a fraction of the Planck mass? Will we get another behavior?
So you are asking whether I should be able to interpret these strong corrections that I get from the strong coupling, right? Because there is from non-renormalizable theory and strong coupling. Whether I can interpret them as simply renormalization of the Planck mass. No, you unfortunately cannot, because theory is not renormalizable. That is the story, right? In renormalizable theory, you can play this game. It's not a game. It's fundamental, but you can trade. You can understand this as a renormalization of certain finite number of parameters, right? These divergences. But that's the whole point about in non-renormalizable theories, you cannot do it, because you have to introduce infinite number of counter terms, okay? And so, yeah, unfortunately, you cannot just reduce it to effective corrections. There are certain corrections that if you want, you can interpret them. It's a question of, you can interpret them as an effective corrections to gravitational coupling that you can do. There are certain corrections, but it's not helping you in unitarizing the theory. All right, nothing else, yeah. No, that's not what I'm saying. So the point is, you see, when you are asking whether effects are important or not, of course it's crucial. What is the physical problem that you are looking at? For instance, if you want to understand graviton scattering at solar distances, and you are asking this question, I have two gravitons and I want to scatter them at solar distances. Scattering of two gravitons, of course, is a quantum process. And no way the only way to understand them is through this type of scattering amplitudes. Those will be minuscule, okay? Of course, will be tiny, as I told you, because already at 1 centimeter, this strength is so weak that you can practically you can forget about it for single gravitons. But it doesn't matter. It's a matter of principle. So if you are looking for a particular process, depending on a process, quantum effects may be extremely important, or classical approximation may be good. So that's the point. So it's not, you should not understand as if quantum gravity is not important up until the Planck scale. That's absolutely not true. Quantum gravity may be important. For instance, that's the idea that quantum gravity is for sure important for understanding black hole physics and information properties, right? But there, what happens is that you have collective effect. I don't know if I'll finally get there, okay? All right, so now, so we have this story, and let's try to understand. No, I have to make a shortcut because, yeah, I only have, yeah. Now, okay, we can discuss other properties of gravitons. It's absolutely fascinating. But I want to get to black holes, okay? Because I want to somehow now try to understand, try to ask this question, whether we can understand classical backgrounds, as probably is related with this question. Well, it's useful to understand classical backgrounds as multi-graviton states. Okay, so now normally in, let's say, in laser physics or in electrodynamics, right? We have, let's say, a laser pulse or an electromagnetic wave, which we treat classically. In a perfectly good approximation, it's classical. But of course, we understand that it's not a classical object. It's a coherent state or a multi-particle state of many photons. Okay, so that's what classicality means, right? So classicality means that when you are dealing with the situation of high occupation numbers, then theory becomes approximately classical. Now, this already has the sort of projection in the thing that I said the other day. Remember, we used in this toy model that we had this psi, right? In this toy model, psi, we said that psi was a quantum field. We had this expansion, right? But then we said, okay, let's populate zero mode to some high occupation number, okay? And when we do that, effectively we get some constant, because this is a constant, so we get square root of n, okay, here, plus non-zero modes. This is Bogoliubov approximation. So we allowed ourselves to replace operator by a C number when the occupation numbers were large, okay? And this is basically the core into, this is a core of quantum to classical transition. So in other words, what happens is that quantum mechanics is encoded in the fact that operators do not commute, okay? They are not C numbers. But this property of non-commuting becomes less and less important when the occupation numbers are high, okay? Right? And so that's why we use this Bogoliubov approximation to replace operators by C numbers. And this is the core. Because if you think, right, any quantum field, right, let's try to refresh our memory. What is quantum field? Quantum field expansion in relativistic case, let's say a scalar or spin 2, that doesn't matter. There is an expansion. Let me restore H bars just to be clear, right? And we have, okay. Okay, so we have this expansion, right? Let's say a real scalar field or the real bosonic field, right? So what's the physical meaning of this expansion? So when we are saying that the quantum field is a set of creation annihilation operators, right? How can we understand in this language relation between quantum field and the classical field? What is the relation? And the relation is, of course, the relation is that when you have a situation when the occupation numbers are large, let's say a coherent state, okay? So as you know, among quantum states, most classical ones for given occupation number are coherent states, right? Because they minimize the uncertainty relation, right? So coherent states are coherent states are eigenstates of the annihilation operators, right? So if I have a coherent state of these are eigenstates of annihilation operator with some phase, which okay, let me call it okay. These are eigenstates of annihilation operators, so they are most classical. So it's already, we can already illustrate the point here, right? So in other words, if I have a coherent state, which is coherent distribution, so I have a state which tells me I have a bunch of photons with high occupation numbers in each mode, okay, certain distribution of modes. So I have electromagnetic pulse, right, with certain distribution of occupation numbers. So a coherent state, let's call it something, which would be some distribution of these guys, sum of coherent states in each momentum, let's say, okay, coherent state. If I take expectation value of the quantum field over that, I get something that what I normally call a classical field, okay? So classical field would be an expectation value of this particular coherent state, in this case, right, of a quantum field. Well, you see immediately what happens right here. What happens is that when I take expectation values, these give me occupation numbers, right? I mean square roots from occupation numbers, okay? And you get the following structure, right? You get h bar, and now watch powers of h bar. That is extremely important. That's why I restored it, right? So you have certain C number factors, right? And then you have expectation value of AK over this coherent state, and this gives me NK, right? So I will get square root from NK with some phase factor plus Hermitian conjugated. Okay, so now we got this expression. Now this is everything is C numbers, right? So there's a classical field with certain Fourier harmonics. So you understand what happens, that each expectation value of creation annihilation operators acts like a Fourier component of the classical expansion, okay, of the classical Fourier expansion, right? Because this is, if I think of this as a classical field, right, which it is, it's Fourier components, okay? So the Fourier components, what I would normally call Fourier components, they are these objects. So effectively what happens, let's group them. So we got h bar nk for each component over to omega k, okay? So now, you understand what happens. Nk over the volume, because I deliberately worked here in the finite volume, Nk over the volume is the number density, okay? Occupation number density. And occupation number density is accompanied by h bar, and this is very important, okay? So, what is the classical limit? Classical limit, now we can understand it, right? Normally we say the classical limit is when h bar goes to 0. Now, who survives when h bar goes to 0? Well, survives states with high occupation number density, okay? So in other words, the classical field means the limit when h bar goes to infinity, occupation number going to 0, okay? If you keep classical field finite, okay? So numbers go to infinity. So therefore, okay, this is extremely important. Why sometimes, many times, okay, in many cases, a classical approximation is good in our universe, despite the fact that h bar is non-zero, right? I mean, obviously h bar is a constant of nature, we cannot change it, it's non-zero. Despite this fact, we know that certain phenomena are extremely well treated classically, okay? What's the measure? Measure is precisely that for those fields or in those phenomena, a high occupation number is involved. Okay? Now, of course you can understand this in the language of action, right? Because also measure of classicality, as you know very well, is action of the process over h bar. If I have a process for which this quantity is small, that process I cannot treat classically, okay? But processes for which this quantity is large, can be approximately classical, right? So in other words, in particular, all the classical processes, they have this property. For any classical process, their action, characteristic action, is typically larger than h bar, okay? And but you can also translate it in the language of particle occupation number. Processes that have high actions, typically they involve many particles. That's why they have high actions, okay? And also, as you know very well, this type of processes typically, okay, they are suppressed. For instance, contribution to the virtual processes from this type of processes is suppressed enormously. Now, why are they suppressed? Because that's precisely the reason why, when we, let's say, compute radiative corrections, if I compute radiative corrections to alpha, let's say, right? Electromagnetic or whatever, or self-energy of a photon, that doesn't matter, whatever radiative correction, right? So you can ask this question, why am I not taking into account here all possible states in between, right? I don't know, some elephants, whatever, right? Okay? You can, in principle, okay? But you don't care because you know that they will contribute extremely suppressed contribution. And that's why we don't care normally to take into account these huge intermediate multi-particle states in our processes, okay? Now, this, okay, I don't want to enter there because the story of this multi-particle amplitude is extremely interesting on its own because there is also breakdown of perturbation theory there because of factorial growth of diagrams and this kind of stuff. Because what I'm saying is that if I want to think of the process that would capture some kind of a production of an intermediate classical object, I don't know, something like this, okay, with many intermediate particles. Okay, so there is a whole story there. Okay, so I don't want to enter. Okay, so this is the dictionary. So the dictionary is that if we want to understand classical processes quantum mechanically, we have to resolve classical backgrounds as multi-particle states. That's the dictionary. That's the way to go. Okay. Now the question is. For sure, this is relatively straightforward for, let's say, a gravitational wave. Okay? So gravitational wave, I can understand as a coherent state of gravitons. Or electromagnetic wave, I can understand as coherent state of photons, or multi-particle state of photons. The question that we want to ask is, why not black holes? Okay? In other words, for sure, I can manufacture a black hole by putting together many soft particles. That's a fact. If you give me a space in this room and I bring a lot of particles, soft ones, one by one even, I can concentrate the energy, which will eventually give me a black hole, right? So it looks like that I can, as an S-matrix observer, I can produce black holes by some initial states of particle states. Okay? Even in two-particle collision, I can produce black holes. If particles have very high center of mass energy and small enough impact parameter so that I concentrate enough energy within the Schwarzschild radius, well, we expect that we form a black hole. This goes back to the work by Toft, Veneziano, Amati, Ciafaloni, and Gross and Mendel. And so from 80s, this was noticed, that was known that this is happening. Then, okay, why not ask this question? Is it useful to trace this all the way? So instead of saying, when two incoming particles come, or n incoming particles come, so we should treat them as particles only until they form a black hole, and then we should treat black hole as something which is not understandable in terms of any particle states. Something extremely special, maybe, I don't know. But why not try? I mean, why not do we try to understand whether multi-particle description of black holes still makes sense, okay? Okay, so there is something there that makes life not so easy, right? It cannot be so cheap that that we are ignoring this obvious possibility for so long, right? There must be something there, and we need to deconstruct what is there. Yes?
So why is it clear that the black hole forms when I put enough gravitons together?
No, here we are using our semi-classical intuition, right? I mean, semi-classically, if you put enough energy within the Schwarzschild radius of this energy, right? So semi-classically, that was the argument originally, but...
The question is about, I mean, I have some conditions where boson stars are false, right? So
Sorry?
why boson stars are so false?
Boson stars.
Yes, so I mean, why can form gravitational constant?
Yeah.
I have to look at, what are they interacted, where are the repulsive forces, and I have particle uncertainty, which is repulsive.
Yeah, sure. So, but
I'm wondering why about they would form.
no, the point is the following. There may be other interactions. So, in other words, this original argument by Toft and Veneziano and these people, right? So it's very clear. So it's semi-classically, the story is following. Let's say I collide E plus E minus, okay? Not even gravitons, E plus E minus. And let's say the center of mass energy, square root of S, okay, energy, is solar mass, okay? So let's say this is equal to the solar mass. And now you say, okay, but let me make impact parameter less than the gravitational radius of the solar mass black hole, okay? So solar mass black hole has gravitational radius, which is Planck square, right? So then the argument is like this. I mean, this gravitational radius is macroscopic, okay? Now I have two particles boosted relative to each other, and they enter in this gravitational radius. There is nothing to prevent them. There is no repulsive force. I can manufacture theory in such a way that there is no repulsive force that prevents it. And if I manage to concentrate this energy within its own Schwarzschild radius, then, according to semi-classical reasoning, a black hole should form. And that looks like a perfectly good semi-classical argument. That's not a proof. Of course, people tried a lot then to understand what is precisely happening. But now, what you are asking is that, of course, if my theory is such that my initial state also experiences some repulsive force, which is more important than gravity, such that it prevents me to localize energy within its own Schwarzschild, of course, then you will not form a black hole. I mean, this is what happens with neutron star. I mean, that's why neutron stars are not black holes, because there are other forces which prevent them from collapse. Yeah?
Just a technical question. Usually you do that calculation with plane wave states, so to get them actually close to each other, you do some kind of smear.
Yeah, the calculation is a big issue, right? So I'm not going there, because there is enormous literature. After that, mostly this was done by group by Veneziano and others. I mean, other groups. I don't want to misquote anyone. So there are many questions there. The questions are, for instance, how do I know that I form a black hole? Okay, what is the calculation that I should do to really see, to be convinced from the point of a quantum field theory that I really form a black hole? And that's highly non-trivial. Why? Because in order to prove that you are forming something in the language of quantum field theory, you need to have a description of that something in the language of quantum field theory. You need to have a microscopic theory of that something. Because if you don't have microscopic theory, you can have a very good evidence. This is what these people had. They had excellent evidence that, for instance, the deflection angle dramatically changes when the impact parameter approaches Schwarzschild radius. So in other words, if the Schwarzschild radius is here, let's say, and I approach impact parameter to the Schwarzschild radius, you see that dramatic things are happening. So in other words, all the precursors of black hole formation, they seem to be there. Okay? But if you want to ask more, what kind of state am I for? You need to have some description of a black hole in terms of particle states. Okay? Now, that's why this idea that black holes are multi-particle states, okay, that could be useful, because then we can look for very concrete amplitudes of black hole formation. In other words, now we can say that actually, in reality, the amplitude that I'm looking for is E plus E minus into many, many gravitons. And now, okay, there is at least there is something concrete that we can try to compute, etc. Now, I don't want to jump over, but actually I don't have much time anyway, but I mentioned in the other lectures, we have done this computation, my collaborators and I, Dieter Stieberger, Gomez, and Reike, is Eisenman, sorry, yeah. For 2 to n scattering of gravitons at large n. Okay, here we have n. And this is one of the evidences. Unfortunately, I don't have time to enter into this, but to me, this is one of the strong evidences that indicates that indeed we are on the right track, at least qualitatively, when we think about black hole as a multi-particle state. Why? Because what we are observing here is, and we use both techniques, string theory, quantum field theory, and you can see that the same computation was also done by Veneziano and Zibianchi. But in any case, so this computation shows that the entropy factor emerges from this computation. So in other words, you see this entropy factor of a black hole, Bekenstein-Hawking entropy factor, precisely when the softness of outgoing quanta is given by the Schwarzschild radius of the inverse Schwarzschild radius of a black hole of the center of mass energy. Okay, which is one of the indications that probably this picture is not completely useless. Okay, so in other words, you see the question is the following. To come back to this discussion in the remaining 15 minutes, question is the following. I mean, sure, we can maybe resolve a black hole as some kind of multi-particle state, but the first question is this useful for anything? And second question is, what are the constituents? And this is very important because, you see, and this I want to explain in the remaining 15 minutes. First of all, right, let's ask this question. When I say that something is composite, what do I mean that it's composite, right? So for instance, I tell you that this table is composite, and you will agree, right? Okay, this table is composite, but somebody can come and ask this question, okay, sure, but why do I care if it's composite or not? For me, this table, let's say, is just one quantum state in the Hilbert space, okay? So it's a quantum state on its own, a table, right? Then why this discussion that it's composite is useful? Okay, we know that it's useful, right? Why? Because I know that since it's composite, I can destroy it with a relatively mild force. Okay, so in other words, there is something in this state that tells me that to think about it as composite is useful. What is that something? This thing is that I can identify constituents, let's say molecules of this table. And moreover, I can say that these constituents are molecules. Now, what does this mean when I say that this table is made out of molecules? Because you may argue, you may say that why should I think in terms of molecules? Let me just think about in terms of a table, okay? The thing is that the molecules inside this table, they are in a bound state. So this bound state makes them off-shell relative to in and out states, okay, asymptotic states, okay, they are counterparts. So this means that somehow when the molecule is in the bound state, relative to a molecule that is free, this molecule is changing, obviously, right? So it is changing its identity. But the binding energy in the table is not so strong to completely erase the identity of a molecule. And that's why it's useful to continue to think about a molecule in the bound state of a table as a molecule, because it's very mildly off-shell. So dispersion relation of a molecule is changing extremely mildly compared to a free molecule when I put it in the bound state. And that's why it's useful to think about this molecule as being in the bound state. Okay? Therefore, something we should understand what happens with if I think about a black hole as a bound state of, let's say I trust this computation of 2 to n, and I want to think about black hole of bound state of this outgoing gravitons, soft gravitons. So what is the criteria? What makes me think that once they form a black hole, it's okay to continue calling them gravitons? Okay. Now, and there is a very clear picture here that we can identify. Now, the gravitons, as I said, they have their interaction strength, gravitational interaction strength. Okay. Now, this gravitational interaction strength, as we said, is given by Planck, in Planck units, their wavelengths. Okay, so now think in the following way. So think in this way, that you compute this amplitude and you somehow, or you manage to bring together many soft gravitons. And then you want to understand what happens at the point when they form a black hole. Now, in this picture, at the point when you form a black hole, this means that they have to form a bound state of their own. Okay? Now, how can they form a bound state? To form a bound state, their gravitational interaction should take over of their kinetic energy. Okay, so they should remain in the bound state. Okay, so therefore, here's the point, right? We can do this estimate in the following way. So let's say I have this bunch of gravitons, n gravitons. I put them together, and I see what happens if I release them. What would they do? Would they fly apart or stay together? Now, you can think about each member of this n graviton story, okay, and n is large, interacting with individuals, okay, right? So I can have one graviton exchange among gravitons, okay, pairs of gravitons, and the strength of this exchange is given by alpha, okay? So pairwise interactions are given by alpha. Now, it's obvious that if alpha is, if their number is small and their wavelength is large, right, the energy of their interaction is not enough. Pairwise interaction is not enough to disturb them, okay? But if there are many, then what emerges is the concept of collective coupling. Okay? So in other words, how each graviton sees the rest collectively. So individual interactions are extremely small, but the collective coupling may be huge. Okay? And this is characterized by a collective coupling, which is sort of an analog of 't Hooft coupling. Okay, I don't want to call it lambda because lambda was a wavelength. Let me keep it like this. So which is interaction strength times the number, occupation number. Okay? Now, you can do a very simple exercise of this sort. Okay? You can ask this question. If I have n gravitons and I take into account one graviton exchange among them, okay? You can compute one graviton exchange from this one graviton exchange diagram. Okay? You can do this estimate. You can ask this question. When the binding energy takes over the kinetic energy of each one. And actually, it happens when this is 1. Okay? So in other words, it turns out that gravitons, they form a bound state when the collective coupling is 1. Now, is this good news or bad news? Actually, the thing is that it's just in the middle. Now, why? Because there are two expansions now that you can do with this system, okay? Now, you know, for instance, that in large NQCD, you can do expansion in Toft coupling, analog of this, okay? Let me call this lambda T, lambda Toft, okay? And, or gauge coupling, which you can trade for this, okay? So I can do expansion in lambda, or, so this means that I can do expansion in lambda and alpha in here, right? There are two expansion parameters. Now, alpha, because lambda is 1, alpha is 1 over n. And expansion in alpha is fantastic. It's like a dream, because it's, alpha, for instance, already for 1 centimeter wavelength, alpha is 10 to the minus 66. So it's like fantastic expansion, okay, right? But the problem is the lambda is 1. So expansion in lambda is precisely where it breaks down, okay? Now, it is true that lambda is not like 1,000. It's really 1, okay? So there is this trade-off. So in other words, the story is the following, to summarize, that you have these n gravitons, okay? And the collective effect is just enough to keep them together. It's not very strong. It's not much stronger than their kinetic energy. So they are not in a deep bound state. They are in a very shallow sort of binding potential. Each of them feels a very shallow binding potential, okay? So their identity changes, but not terribly. So in other words, if I pick up one graviton from this bunch and I say, how different is this graviton, dispersion relation of this graviton, from the dispersion relation of a free graviton that we had there, the answer is that dispersion relation is changed, but by order 1, not by more than order 1, okay? So this means that somehow, good news is that you can still call this object a graviton, okay? You can still say that this is a graviton in the bound state, because dispersion relation is not completely damaged, okay? But in the same time, the trade-off for this, that dispersion relation is minimally changed, because that's the minimum. You cannot do any better, because before that you would not form a bound state, you see? So what black hole exploits is really a threshold of bound state formation. Okay, this is the absolute minimum that you need to keep gravitons together, otherwise you cannot keep them together. And so there is a trade-off that, of course, you have to break perturbation theory in lambda. Okay? So then, to summarize here, now there are certain things in this picture, since there are some expansions which are valid, and some expansions that require some technical thinking, okay? We can try to check certain predictions of this framework in the corner of in the regimes where we can understand it, okay? For example, Hawking radiation. In this picture, you can immediately understand why Hawking radiation should be there. Because black hole is a very shallow bound state of gravitons, and they constantly leak out. So you can estimate the rate. So the rate is very simple. You have a bunch of gravitons, the two scatter, and one leaves the bound state. This is the rate, okay? Now we can understand this rate immediately, estimate. Because this rate goes as alpha, this is controlled by alpha, so the rate of emission goes like alpha square, gravity, times the number of pairs, which scales as n square, and times a typical momentum transfer in this process, which is, of course, is given by h bar over r. That's the emission rate, okay? And this is 1 over r. This is precisely Hawking emission rate. So this immediately you predict that there must be Hawking radiation, because it's a result of the fact that you put gravitons together, but quantum mechanically they rescatter. And this rescattering pushes some of them out. Now, of course, you also immediately predict that the Hawking radiation should be soft, should be of the same softness as the composite gravitons. So it should be picked around a maximal softness of the bound state. Okay? So you immediately understand qualitatively this picture. Okay. What else? In the remaining 2 minutes, for instance. So there is a list, in other words, what I want to say that there is a list of phenomena that this picture immediately predicts and tells you that you should see something there. For instance, immediately this picture predicts that there will be deviations from thermality of Hawking radiation. Immediately, what are the deviations? The deviations are, actually, you can just very easy, is 1 over n. Now notice that 1 over n, right? What is 1 over n? 1 over n is 1 over n is alpha, right? And this is, right? What is it? This is L Planck square over R square. This is precisely 1 over the Bekenstein-Hawking entropy. Okay. So this picture immediately predicts this deviation from thermality. And I told you in the previous lecture, I think I told you, that this deviation from thermality you can predict without any microscopic picture. Okay? For a generic black hole. Why? Because if I have a black hole, what do I have? I have, this is Stefan Boltzmann law for black hole evaporation, right? And temperature of a black hole is 1 over R. And R is m squared over m Planck squared. Okay? So now we have everything. These 3 equations immediately tell you that T dot, the time dependence of temperature, over T squared is 1 over precisely the entropy of a black hole. You can see it from here. Okay? Which is the same thing. This is L Planck square over R square, or which is the same thing. You can write it in terms of a black hole mass, m Planck square over m square. Now you see that there is an absolutely general prediction about this, just simply from Hawking radiation without any microscopic picture, right? Now, if you don't know the microscopic picture, you may get puzzled because, look, this tells you that clearly there are deviations from thermal radiation. It cannot be thermal because T dot over T square is precisely what I call semi-classicality parameter or thermality parameter. This is what controls the level of semi-classicality of your radiation, level of thermality. Since T dot is non-zero, your radiation cannot be exactly thermal. Because you can prove, I've shown this in certain discussions, that in papers, that you can prove that there is no system with available degrees of freedom which would match what we know about black holes that would thermalize instantly. That is impossible. So the only possibility for you to say that temperature changes but radiation remains exactly thermal is if your system can thermalize instantaneously. There are no such systems in nature. It's impossible, okay? Because thermalization takes time, no matter how strongly how strongly correlated your system is. So therefore, this is of course an indication. But this you immediately recover from here. Because of course, once it's a bound state of gravitons and once the thermality is simply rescattering, not simply, profoundly rescattering of gravitons that leave, this is a prediction of this scenario. So this scenario predicts that the black holes must have, we even called it 1 over n hair. So this fact that Hawking radiation encodes corrections, 1 over n, okay, there are corrections, this is 1 over n hair. Now, strikingly, in the previous lecture, this 1 over n hair here is very similar to 1 over n hair of this holographic system that was relieving this pattern to the external radiation, right? So again, we see a striking connection there. Now, let me finish. If you give me 1 minute, where is it? Yeah. Let me finish, or 2 minutes. Sorry. If you give me 2 minutes, let me finish with one more effect, so-called species story. Now, because in semi-classical computation, Hawking radiation is thermal, is almost thermal up to this tiny correction. we know that black holes evaporate democratically in all the particle species. Okay? So therefore, this means that this law of black hole evaporation, this t square over t dot over t square, has to be corrected by number of species. Now, what does this mean? This means that if you have many species, black hole, the scale or size of a black hole, beyond which black hole goes out of semi-classical regime, is bigger. If there are many species, then large black holes already will become non-semi-classical. And by the way, you can establish a bound on all possible species in nature at low energies. And this bound is, of course, it's huge. So in other words, but it's still finite. So species 10 to the 32 is the maximum. So you see, it's very nice. It's absolutely beautiful that black holes, they control all possible species that could exist in the hidden sector. So we know that just from the fact that we didn't see quantum gravity at LHC yet, okay, the number of species cannot exceed 10 to the 32. Of course, this is a huge number, but it's still finite. Now, by the way, I even had a proposal to solve the hierarchy problem by postulating that there are this number of additional species. So this is true, because if you have this number of hidden species, then the quantum gravity scale comes down to around TV scale. So this will be one very nice solution of the hierarchy problem. So if we have hidden sectors, 10 to the 32 copies of the, let's say, standard model or whatever, okay? That's not excluded by any phenomenological observation because the only connector is gravity, and so the only connector are black holes. So this will solve it. Now, coming back to the species, so there is the species thing, and so the scale where gravity becomes quantum is no longer a Planck scale, but it's a scale from this argument, and Planck divided by square root from number of species. Okay? Now, question, how can you understand this in the theory of the composite black hole? Okay? The black hole is just a bunch of gravitons. Immediately, black hole explains, this picture explains this. Why? Because, from what we saw, graviton couples universally to energy momentum tensor. So graviton couples universally to energy momentum tensor of everyone. Okay? So therefore, no matter how many hidden sector species you have in your theory, this diagram will get corrected. So now, on top of this diagram, there will be a diagram in which gravitons would emit all the species that are there. Because this coupling is universal. So on top of this amplitude, you have n copies of this on the amplitudes, each propagating different species. Okay? Now, no matter what species you have, you can always pair produce them. There is no conservation law that allows the decay of species. You want your pen? Yeah, no problem. Okay. And so you see, also this is automatically encoded there. Now, I have to stop here, unfortunately, or fortunately for you, because there is a long list of other things that this picture immediately tells you that you can understand. So, to summarize, my summary would be the following, that I think that to try to understand so-called classical and geometric backgrounds as multi-graviton states is really useful because that's the key, one way to think about why black hole, again, this is manifest here, right? You see immediately that, of course, if black hole is a bound state of gravitons, there is no information loss, although for a naive observer, because this naive observer measures Hawking radiation and cannot measure 1/n corrections because they are tiny, this looks like there is no information. But there is information. It just requires reading, and this reading precisely requires time scale, which I didn't have time to discuss now, which is so-called Page's time. This precisely also predicts why you should start reading the message which is stored in black holes after page's time with order 1 rate. Okay? So I think that's the connection to go. So then therefore, in these lectures, unfortunately, I could not get to cosmology or anything even near. So these two messages I want to reiterate. One is that independently, whether you think that to think about black holes as multi-graviton states is useful or not, independently of that, there is a fact, which I tried to demonstrate in the previous lectures, that information processing of systems with enhanced memory capacity are universal. We saw that they have literally the same properties as black hole has. So there is some underlying universality. This universality is very nicely explained if we think about the reason for this universality is nicely explained if we think of black holes as multi-graviton states, because then they tell you, okay, this is simply systems of enhanced memory capacity are multi-particle systems at the critical point, and critical point is this. But that's secondary point. If you think that this picture may or may not be useful, of course it's a question. Still, there is this universality, and that's a separate statement. Okay, this universality is a fact that has to be understood. Okay, let me finish here. If there are any questions, of course, I'll be happy to take.
How can you use the calculations in the end for black hole formation? So in the beginning we expanded around Minkowski and assumed that this.
Yeah, this right. So did you finish the question? Yeah. So yes, here the picture, as I said, here the picture is. So you see, in quantum field theory, there is this question: what is the there is the question of choosing what you want to call the vacuum state. Okay. Now, the vacuum state doesn't have to be an exact vacuum state; it could be approximate. For instance, today we live in the universe in which things are changing. So, for instance, there is dark energy. This dark energy may be changing, but despite this fact, we are not bothered by doing computations for LHC as if we are in the vacuum and this kind of stuff, right? So, as long as your background is mildly time-dependent, mildly compared to the problem that you are asking, okay, you can choose this background as a vacuum state. Okay, so therefore, you can think in terms of a black hole background as your vacuum and do computations there, right? So this is what Hawking did. Hawking chose this limit in which black hole is infinitely heavy, is eternal, and computed radiation as a vacuum process. This is one view. Now, this is a different point of view in which I'm saying that for me, I don't want to view black hole as a vacuum state because any finite mass black hole for an S matrix observer, for a particle physicist, is a resonance. It's an unstable state, which is, you can view it as approximate vacuum if your problems are short time scale problems. But the information recovery cannot be a short time scale problem. Okay? That's obvious. I think that's trivial because if I tell you that there is a house and this house is encoding some information, and I want to understand how information comes out when I demolish the house, you cannot sit there for 2 days and say you did computation while your house is a vacuum. You cannot do it, right? Because the time scale problem that you are asking exceeds the time scale of your computation, So therefore, what I claim is that to understand information story for a black hole, we need to choose a vacuum which is more eternal than the black hole lifetime. Okay? This is statement number one. Because if we don't choose that vacuum, we will not be able to understand information recovery. I think it's almost a triviality what I'm saying. Okay? So therefore, for me, the black hole is a state on an eternal Minkowski vacuum, which I can construct. And my question is, what is that state? First, and secondly, whether it makes sense to think of that state as a multi-graviton state. Because if it's made out of gravitons, it should be a multi-graviton state. Maybe it's not made out of gravitons. That's a separate story. We can think that black holes are completely independent states, completely independent degrees of freedom, which only appear there once the black hole is formed, and they don't manifest themselves in everyday life. That's one point of view. I don't share that. I think that black hole degrees of freedom should come from the binding of gravitons, etc. Yeah, so this is the approach. So for me, the Minkowski vacuum is the eternal because that has the time scale much longer than the information recovery time. And this is my obligation to choose that as a vacuum. Right.
Okay. May I ask then one additional question?
Yeah.
And then the H mu is not small, right? So,
On the black hole.
yeah, no, on the Minkowski background. I mean, if we
On the Minkowski, no, the graviton is the excitation that you are deriving by first doing linearized gravity in this approach, right?
Yeah.
We do linearized gravity, and then we quantize this linearized gravity, and we think it's in terms of gravitons. Now, the deviation compared to Minkowski may be small. For instance, gravitational field of the Earth is 10 to the minus 7, as I said, but it's still classical. Because the question is not how big is the deviation. Question is how many gravitons does it contain. If the number of gravitons is large, it's approximately classical. If it contains only one graviton, you cannot treat it classically. So if I give you a graviton of Planck momentum on a Minkowski background, you cannot treat it obviously classically. It's just one graviton with a huge momentum. Deviation could be small in the sense of particle number. This means that amplitude is small, but the momentum may be large. So we have to distinguish these two things, right? Because remember, in the geometric thinking, we are distinguishing between high curvature and strong field. So if I give you a gigantic black hole, the curvature around this horizon is tiny. I can make it arbitrarily small by taking black hole large. So curvature invariants, they vanish when black hole mass goes to zero, goes to infinity. But gravitational field, of course, is always strong because as compared to Minkowski, from an outside observer, obviously deviation is huge. So you should distinguish between high curvature and strong gravitational field. And the high curvature, this has counterparts in particle description. This means I should distinguish between high momentum gravitons and many gravitons with soft momenta. These are two different things, okay? Yeah. There was something there, yeah, go ahead.
So I don't quite understand. How does your model of information recovery evades the action of the small corrections theory?
What is small corrections theory? I don't know.
By Laffour, which says that you cannot make the page curve decay just by applying some small quantum corrections. Because as I understand, you have precisely the small corrections.
Well, I have small corrections at the beginning stage of the operation. Remember, I explained yesterday's lecture, right? So I showed that there are two things. When the black hole emits radiation, you can ask this, how much of the imprinted pattern is gone with this radiation? And I told you, all the time, there is 1/n very blurry image of this pattern going out. But if you are an outside observer, this small correction for you is not enough to resolve this image up until very late times. However, late times, another process sets in because the pattern becomes unbearable. And then the information flux is much bigger. So it's no longer a small correction. There are two different effects. Okay. Already at the beginning of evaporation, my claim is, already at the beginning of T equals 0, you form the black hole and T equals 0. And T equals 0, you start observing Hawking quanta. I claim that already there you have corrections 1/n. And that I'm proving because that's the expression there. T dot over T square is non-zero. And I have that you can go through the proof. There is no system in nature which can thermalize instantaneously. Okay? So if temperature changes, any system will take some time to thermalize. So this picture gives you a microscopic explanation of that, why that's the case. So it tells you that from the very beginning, you will have small corrections to Hawking radiation. Okay? Towards the very end, obviously, once you diminish the black hole, another process that I discussed yesterday sets in, and that's a different process. The pattern simply becomes unbearable for a black hole. Okay, so those are two different things. Yeah, thanks for asking.
So, what about the phenomenology of bound states? Because you're looking at spin 2 bound states, right? Or spin 2 particles.
Yeah, for gravitons, yeah.
So, how would it change with spin 1 or spin 0 particles? Because
Yeah, that's an excellent question. Yeah, so for instance, we were trying to understand whether similar phenomena could happen in theories of other spins. For instance, for spin 0, and we even had a proposal with Cesar Gomez, Jan Judice, and Alex Kehagias. We called it classicalization, because our idea was that if in the standard model similar things could be, let's say, formed by Higgs or longitudinal W's, then those could behave like black hole-like in a sense, and maybe they could unitarize the amplitudes. Okay, so it's an open question. Yeah, absolutely. So I'm still thinking about that, and okay, I know other people are also thinking. So in other words, how far does this class of theories goes? Now it looks like that it's not empty, because as I showed you, these holographic models, since they have all these properties. So you,
let me say one confusing thing I find.
Yeah.
And I think about boson stars. So they're usually huge objects in comparison to say the structure.
Mm-hmm.
But I can make them smaller, more compact by cranking up the coupling, say of scalar fields.
Mm-hmm.
And now this seems to be somehow happening in spin 2, yeah? That you have a very compact object, right? You have a black hole.
Well, it's compact, yeah. It's compact in the sense that again, you see, this is the we should not confuse. First of all, I'm not an expert on boson stars, but okay, laws of nature are similar for different things. So you see, as I said, if I think about a gigantic black hole, right? The curvature already in semi-classical theories, curvature invariants for a gigantic black hole are tiny. So we can say that it's compact, but it's compact in which sense? For me, the compactness of that object is, we called it maximal packing. Maximal packing is this. I say that for my definition as a quantum field theorist, definition of compactness would be, if you put constituents, that number that exceeds their inverse coupling, I would think of this object as compact. Although the curvature invariance may be tiny, because the objects may be very soft, you see? By the way, if you extrapolate, if you take a limit of an infinitely massive black hole, in that limit, near horizon geometry becomes Minkowski geometry. So we can think of Minkowski space, paradoxically, if you want, as a limit of an infinitely massive black hole. So from that point of view, Minkowski space, you can think of it as maximally packed space, because it has infinite entropy, because it's like an infinitely big black hole. But of course, it's not really dense. So in other words, I would distinguish between energy density and compactness. These objects are compact from the point of view of occupation number, high occupation number of soft modes. That's the compactness that I would. No, it would be interesting to see if, for instance, these boson stars, etc., they exhibit some of these phenomena. So you see, when we do this construct model building of these compact objects, of course, one thing we have to be careful is not to make theory strongly coupled in terms of alpha. So that's very important, because sometimes we can get these pseudo solutions which classically look like they are solutions, but in reality the coupling is strong, so they cannot be trusted. There are many solutions like that. So for classical solutions to be trusted, this is a necessary requirement that the alpha should be small. So then we can trust the solution. Yeah, so that would be our guideline. Yeah.
How do you describe, one last question, how do you describe the chocolate open framework?
Yeah, very interesting question. Yeah, so okay, I didn't try to really describe them because I already have enough brain occupation with the neutral ones. But yes, so we were thinking sometimes how to. So yeah, obviously there would be. So the charged black holes in this language would be black holes in which not just gravitons are present, but also other species like photons, for instance. Okay, so there would be a bound state which also there is an admixture of photons in this bound state, such that they form Gauss's law. So there must be some kind of a mixed bound state between black hole and photons. Now, of course, you can trivially get charged black hole in this picture if you simply say, okay, let me take this bound state of gravitons and throw in a source which is charged. Of course, that would be like an obvious way to get a charged black hole without even bothering with resolving photons as multi-photons or whatever. So, of course, there is this one simple way to do it, but maybe there is some more to it. So, in other words, maybe the charged black holes can be thought as some kind of electrically charged. One thing, for instance, magnetically charged black holes, I would think that they somehow also contain some excitations of non-abelian fields in the bound state. These are very interesting questions. Yeah.
Okay, I think in view of the time we have to stop here. I have three small announcements to make, but let's first thank you for the